Assalamu alaikum. Myself, Mariam Ali. Today, I am going to explain you about Karnaugh maps. So basically, the main things I am going to explain in this video are how to simplify a boolean function of 3 or 4 variables by using Karnaugh maps. The second thing is the implementation of those equations of Karnaugh maps into a combinational circuit, converting a truth table into a 1D truth table into a 2D truth table. So before going into it, let's get to know why we use this K-map instead of using the Boolean algebra theorem. So basically, those Boolean algebra theorems and De Morgan theorems are time-taking. So we use these K-maps for simplifying a Boolean function. So how these Karnaugh maps introduced? Karnaugh map introduced by a telecommunicational engineer at Bell Lab. So while exploring its new technology of telephone circuit, he invented a graphical way of visualizing and then simplifying Boolean expression. So those things are known defined by this person here. So basically, what are Karnaugh maps? A Karnaugh map is a collection of squares, and those collection of square here, the collections of square and those collection of square are the graphical representation of Boolean function. The next thing that how to visualize a K-map, or we can a K-map viewed as. So this is a truth table. This truth table is in 1D form and this K-map is in 2D form. So we can say that K-map is a reorganized version of truth table. The K-map also referred as a 2D truth table. A K-map is nothing but a different format of representing the values present in the one-dimensional truth table. As it is clearly shown that let's study here that how we implement this. In this we define as 0, 1, 2, 3, 4 up to so on like simple table. But here it contains a specific way of defining this. 0, 1, then left here, 2, 3, 4, 5, 6, 7, 8, 9 down here, 10, 11, 12, 13, 14, 15. So it is representing the 2D form, so that's why it defined it like that here. These are A complement here, these are B complement here, C complement here, D complement here. So let's get a standard conical form. Just now we are not studying these Karnaugh maps right now. We are just studying how a conical form that SOP formed by a truth table. So, and what are the main terms and the max terms? So basically, main terms we can say that it is defined as AND term or multiply, and these represented as a plus sign. When we wrote this as plus, if we wrote a function xy plus xy bar, then those are the sum of products. And if we write x plus y multiply x minus y, so these are the product of sum here. So that are the min terms and the max terms. As the dot represent n, so we said that the min terms are n terms and plus represent r, so we say max terms are r terms. Let's get this circuit. So this is a simple truth table here. M0, these are the A, B, C, D here defined by its here. How this min term form now? If we see this circuit here, this 0 here, it is A bar, so this A bar here, so and this is C bar here, D bar here, and the B bar here. So from all sides it is A bar, B bar, C bar, and D bar. So this is how we wrote it A, B, C, D. So this is this collection of squares, the collection of squares here as we defined here. The K-map is a collection of square, but if we see here, this square contain a single min term. So this is how this further min terms form. This is a truth table I formed here. I represented a function here. So that function contain 1, 1, 1, 0, 1, 1, 0, 0, 1, 1, 0, 0, 0, 1, 1, 0. So according to this thing, how this form? As all 0, we can write this equation like that too. All 0, A bar, B bar, C bar, D bar. The next thing is here. Where are the excluding 0? Here 0. Like there, this in this line, the function gives 0. So we don't consider it in our SOP terms. The SOP terms contain only for those having 1. So we form this equation as we introduce here that how to form a equation here. Now how to implement a circuit by using these terms here. I implement this circuit on the proteus here. So let's get here how the circuit is implemented. So as in the practical, we are not using the logic probes and logic states. So I use this DC probe by clicking it here. This I get my generators. I get DC supply here, provided this DC supply, and other things are provided by this component here. These buttons, NOT gate, a 300 ohm resistor, and LED here. But the further things are the gate here. These all are the 4 input AND gate and other are the 3 input OR gate here. So as all numbers contain the 4 digit, so I took a 4 input AND gate here. Now how to implement these SOP form that formed by that K-map thing, or we can say by truth table. So here the first input is provided by as it is A bar, B bar, C bar, D bar. So first provided by this not coming here, A bar, B bar, C bar here and the D bar here. This is how further let's do the last thing, A, B, C, D bar. So this is how I implement A here, A coming from here, B, C, and D. Those resistors are connected parallel to these switches here, and further these switches, one side is attached parallel or parallel series to this DC voltage. I provided a 15-volt DC voltage here and this 300 ohm resistors here in the parallel, and the further these input are coming, these three are adding, these three things are adding, then these three are adding, then these three are adding to these one A B OR gate, and these OR gate are further converting here as it is as 9 input OR gate is not present in the proteus, so I took the single 3 input and then combine it here. Let's test it that it works properly or not. I run it here. This is the truth table here. Let's check this condition on this 1 0 0 0. At that the LED must be on. 1 here 0 0 0. LED must be on. Let's check another condition where LED is off. Let's do that. 0 1 1 0. 0 1 1 and 0. When the switch is open, it represents 0. When it is at that state, it is on. So here you can see the LED is off, that represents 0 here. Let's check the last condition. 1 1 1 1 1 1 1 and 1. At that the output must be 0, so the LED is off. This is how we simply implement this main terms in the SOP form. I implement this circuit, or we can say that I implement this SOP equation in the Karnaugh software too. This is how I implement this circuit. I implement this circuit by using its terms like this for like this condition, this condition for the NOT gate, this for the and this symbol for the OR, this for the NOT and this for the OR gate. So this is how I implement. As OR gate is connecting here, you can see 1 2 this here, like all input 1 2 3 4 5 6 7 8 9. The 5 are represented here. 9 are. I already compiled the study, and here is RTL viewer. As it is software viewer, which is a little bit different, but we can see that these coming NAND gears and this combined into this OR gate, these 9 OR inputs. Let's get into the waveform of this circuit. Node finder, let's implement this list. Okay. To run this, implement here as we define it here, like D as the least one, and to get it the most at A. So the most at A, let's get it, for example, 800. Then the half of its period at B, and the half of B period at C, and that half period on last D. And then run this waveform, save it, and run its simulation. Slow progress. It's gonna take some time here. This is the implemented. Like here we can see when these ups contain on, this contain off, on, off here like that. So let only get D here 0, 1, 0. In the first three condition here, the function is at on state. Let's study it is on or not. Here, the 1, 3, it is on, then 0, then the 2 are on. Here, then in one condition 0, and then on for 2. Then off for 2, then on for 2. And then off for 3, on for 2, off for 1, on for 3, and let's so on. This is how this implement here. Let's get into the K-map circuit, that how we form that K-map. Now how this reduced simplified equation formed here. So this is a K-map I formed. Let's get into this by here so we can easily study it. Okay, this here. Now as here we can see that in the truth table here. These are the, as we studied above here, like 0, 1, 2, 3. Okay, so we implement it here as it is 0, 1, 2, and then 3. So this is how that implement here. Now further, the main thing how to form a K-map, let's read those steps the above and then form this. The first step is select a K-map according to the number of variables. As the number of variables in our truth table are 4, so we selected a 4 cross 4 K-map. Identify min terms and max terms as given in the problem. We identify these min terms and max terms here. Further, put SOP in one block. K-map represent as a min terms here, and that code for PS. As we are studying SOP here, so our focus are on it. And this is how further, and rectangular groups are formed in the even order. We don't form it in the odd order like 3 pairs. That is wrong for the K-map. We form the 2 pairs or the 4 pairs like that. This is now we ignore the 0 1 cause we are studying the S to form SOP form, so we don't okay. If the one is single, then just click it as single. If it is some pair form like here, the 2 form 1 1, so we paired it. These are the fourth, as 4 is the even, so we took a 4 pair even. We can also contain it paired like that of 4, like here 1 1 1 0 1 4 5, a pair of 4 5. Then here the pair 0 1 pair, then a single pair of this one corner. The pairing here are 0 1 4 5, 0 1 4 5 pair here contain the AC. How it contain AC now? As here in the whole here, the A is common and a C bar is common. As it contains D bar here, so we ignore it. It contains B and B bar, so we ignore it. The common one, we took that as the A bar, C bar. The next one is 0 1 8 9. These 0 1 and 8 9 are the similar pairs and are containing So we combine it and let's get its function. How it function form. It's here are a bar. Now studied here what is common here. A bar, B bar, A dot B bar. So A bar and A are not common. So we took the B bar common as here and dot it by the common thing as in the column here. C bar, D bar, C bar, D. So the common is the C bar, so we took that. Similarly, 1, 5, 9, 13. 1, 5, 9, 13. So for that, from all here, nothing is common as something is different for that. The only common thing is this column statement C bar D. So we took that. The next is 0 and 2 as it is in a single row, so we took that thing and the common thing in is that is D bar. So A bar, B bar and D bar. The C and C bar are different, so we don't took that different thing here. The last thing is this 14 combination that is a single one, so we just took it as whole A dot B dot C dot D bar here. So this is how these the functions or the common things in our pair form, we just add them and wrote it as a function. So how to form this that circuit is also formed like we formed before. This is how this circuit form here. Let's run it and check if it's true or not. For the condition, let's get this condition 0 1 1 0. Let's run it 0 1 1 and no sorry 0 1 1 and 0. So LED is off here. It must be off that to represent 0. Let's run for the 1 1 0 1 1 1 0 0 and 1. For that LED must be on to represent 1. So that's how I implement this circuit. Is also implement like before that a 300 resistor is added to all switch in the parallel form and 15-volt DC voltage is applied, and as R of 5 input are present, so took that here and run it. Like I form a standard equation for that SOP minterm. I form a key map Verilog code for that too here, like this here. C bar D, this represent for the NOT, this represent for the and this represent for the OR. So that's how this implement here. As you can see, A bar C bar. So A bar C bar here. This A bar C bar. Let's get here. If we implement it here as A bar and B. So that's how we wrote. And for that plus sign, we wrote that like this sign. So this is how these circuits implement and those Karnaugh maps things formed here. And the output as both are same. One is a simplified one and other is without simplified. So both input and output must be same. So today we learned how to implement a K-map by using the truth table and how to perform how to get circuit equations from a K-map, from a truth table by using minterms, by using maxterms. So we can see that our Karnaugh maps are helpful and are used for simplifying a Boolean expression, or we can say a long statement like that here. This long statement by the truth table minterm into a very simplifying form just by looking at this table columns and rows here. It is not necessary that for every Boolean functions or for every number of rows the columns and rows are equal. It is different for different variables here. Like if we do it for the three variables, the three variables are here like that. So x, y and z here. So x bar, y bar and z bar. So that's how truth table. So it is not necessary that the rows and columns for all the truth table are equal, but we form it by here at the power. As for the number of rows and columns 2n, as we have four variables here, so we took 2 raised to power n, so we have 2 raised to power 2, we get 16 here. So we wrote 16 variables column. So for the three variables, we wrote like here 2 raised to power 3, we get 8. So this is how Karnaugh maps form here. So hope so you understand it, or understand this graphical method of representing a Boolean expression or rewriting a 1D truth table into a 2D truth table. Thank you.